if you have, these are you hopefully have around your home. So we would like a 2-liter soda bottle, a 1/2-inch diameter of PVC pipe, paper, scissors, tape, also coffee or tea, and creamer, and then also some magnets, 1 AA battery, and a piece of copper wire longer than the battery. Our presentation today will be our mad scientist running these experiments today will be Divya Illumalai. He is an associate professor of physics. Divya.
Thank you, Andrew. All right, let's begin by the simplest one, right? The one that involves a Coke bottle. So that's a 2-liter Coke bottle that I have. I drank all, well, it's a Sprite bottle. I drank all the Sprite this morning. So I'm a little high on sugar. That's okay. I have a 1/2-inch diameter PVC pipe. So I went this morning and I got this again. Now I seem to have multiple sections of PVC pipes, unfortunately. So this is a really nice little setup. So if you buy a 1/2-inch PVC pipe, right, the awesome nature of this whole setup is it fits perfectly into your 2-liter bottle. Okay. So I went ahead and put some tape around that just to hold my pipe. Put some regular tape, right? So I took a length of the tape and I put it around my PVC pipe to hold it in place around my bottle. So this experiment we do in our class, and the way we do this experiment is really cool. We buy pizza, well, I buy pizza, and I buy them soft drinks. So we eat the pizza, drink the soft drink, and then we have these bottles, right? So this is in our continuity equations class. So when we're discussing Poisson's equations or Bernoulli's equation or continuity equations, that's the class we do this experiment in. And so the whole idea behind this lab is to prove that the continuity equation works. I'm going to show you a slide in a little bit, but before I share the slide, right, well, let's do this cool experiment. So step 1, drink the Sprite. Step 2, place the pipe inside the Sprite bottle and a decent length, right? I've not put in too much of it inside. And make sure to tape the top end with any kind of tape. Doesn't matter what kind of tape you use. Just take a little piece of tape. All this does is it makes sure all the air goes into the pipe, none of it escapes out, and it also holds the pipe in place. So now we have created our rocket part, our reusable rocket part. We're all Elon Musks at this point. The other thing we want to do is create our paper rocket. Okay, the way we create our paper rockets, pretty easy. Take a sheet of paper, any sheet of paper, fold it in half, tear off because each sheet of paper can make 2 rockets. And you know, eventually in a class full of students, that becomes pretty contentious. Rockets are prized possessions. So the next thing we're going to do is we're going to roll this little piece of paper around our pipe by making sure that there is a little bit of the paper extending above the pipe, okay? Just a little tiny bit. All right. So I've made 1 roll. I have a pair of scissors somewhere here. I'm going to cut off this excess piece of paper. So now I have a piece of paper wrapped around my pipe thus, with just a little bit protruding above the pipe. I'm going to take a piece of tape and tape it in place. Right? Put this tape on top of the paper, not on top of the pipe, otherwise then it tends to stick to the pipe, and we don't want that. So all I'm doing is I'm making sure that the cylindrical shape of this paper is retained, and it's free to move above this pipe, okay? This next step is easy enough. You fold the extending part of the paper into the pipe. Just fold it in.
You just fold it in.
Yep. And technically you have made your rocket, right? It'll fly. At this point it will fly. But if you want to make it a little bit more fancy like the one I made it here, we're going to give it little wings. To give it wings, take any little sheet of paper that you have and fold it such. Okay. This is not perfectly square. If it was a perfectly square piece of paper, it would have folded perfectly, but it's not square, and that's okay. I want to cut off the excess little bit. Take 2 pieces of tape. Actually, here I took just 1 piece of tape, trying to be conservative. All right, now I'll go look for my little rocket. So here's my rocket. I'll place this little piece of paper adjacent to the rocket and tape it in place. So the easiest way to do that is to tape this piece of tape, or put the piece of tape on the piece of paper like this, you know. Half of it's on the paper, half of it's off. Now the other part, I'm just going to stick it onto my little rocket. So that's one wing. I can reinforce this wing by taking another piece of tape and doing the same thing I did to the other side. All right, so here's my little rocket with 1 wing. We're going to actually try what happens if you have a rocket with 1 wing too. Why not? So let's try first a rocket with 1 wing. Okay, all you have to do is place your rocket back on top of your pipe, right?
And this is the part where we recommend you clear the room or give safety goggles to everyone in the room or have them sign an indemnity waiver. Thank you very much, TCC Legal Department.
Right, so when I'm doing this in class, all my students are wearing safety goggles. I forgot to mention that. There's nobody here except the dogs, and the dogs really don't care. They're excited when I have bottle rockets. So, normally, if you have children around, make sure they're in safe locations. Don't point this at them, hopefully. All you have to do now, there's 2 ways you can launch this. The easiest way is to put it under your armpit and simply launch it.
Ooh, yay.
Turns out it flies pretty good with just 1 wing. Not bad at all.
Did it corkscrew? What direction did it go with the 1 wing?
It went towards, okay, yeah, but that's kind of logical, right? It went towards the heavier side. It leaned towards the heavier side and went towards the left. Wait, sorry, right. And now it won't even fit back on there. Oh, there you go. Let's try one more time. That was pretty cool. So the way we do this in class is we have competitions. All right. I thought about having a competition right now, and then my wife was like, "Really? Take me out to dinner." So the way we do this in class is we have competitions, right? And whoever wins the competition, and the competition is how far you can launch a rocket. So you can do whatever you want your rocket, modify it any which way you want it to. And the furthest your rocket goes, I mean, if you launch the rocket that goes really far, you're the victor. And the winner gets a gift card of sorts. Of course, not from TCC, from me. So that's a really cool experiment. So what is the idea we're trying to convey here, though? The idea we're trying to convey, let's try to do this. There you go. Hopefully you can see my screen. If not, please just let me know.
Yes, we can.
Awesome. So the idea we're trying to convey is that continuity equation. The simplest explanation for the continuity equation is this. So when you go out in your garden, and I have a garden hose, and me and my daughters, we play with it quite a lot. So when you turn on the garden hose, there is a certain flow rate, if you would. Water is flowing at certain amount per minute or second. One way you can increase the flow rate is by placing your thumb on top of your pipe or tube. When you place your thumb on top of the tube, right, you suddenly notice that the water shoots out farther. Its velocity increases, and it seems like it's flowing faster. So what are we doing here? So continuity equation basically states this. This is the relation for the continuity equation, right? Rho 1 A1 V1 equals rho 2 A2 V2. Rho being the density. A is the cross-sectional area for your flow channel, and V is the velocity of the flow, whatever is flowing, water in this case, or in this case, air, right? So when you put your thumb down there, what you're doing basically is you're reducing the cross-sectional area. So to balance out this equation, the density doesn't change. Water's density is more or less a constant, right? So density of water is constant. You just reduce the area. You halve the area if you would. So what do you think happens for this equation to maintain its steady state, right? So for the flow to continuously not happen, the velocity of the water that's coming out should double. Because the area is half, the velocity of the water should double. And that is exactly what happens. The velocity increases, which is why it is able to travel further out. Shoots out, right? It's a fun little experiment. If you have dogs in the yard, right? Turn on the water to fill their little bowl and then just do that. See them run. It's fun. So this is the experiment we do in our continuity class. The whole point is not eating the pizza or drinking the soft drink. The point is to get the idea across. So here's what's happening in our little experiment. We have a bottle with a lot of air in it. We are forcing all that air to go through this little tube whose diameter is much smaller than the diameter of our bottle. So all the air in this bottle is being forced to flow through this little thin pipe, right? So using our continuity equation, or the idea of our continuity equation, the velocity of the airflow through the pipe should be much larger because the cross-sectional area of the pipe is much smaller than the cross-sectional area of the bottle. And if you put a capped little rocket on the top, that air coming out with a much higher velocity is there's going to be a velocity transfer of sorts. All that velocity is going to transfer to your rocket, thereby shooting it out. The furthest we've got people shooting this rocket, the longest distance we have got in our classroom is about 75 feet.
Oh, wow.
So here's my challenge to you. Design a rocket however you want to. And in our discussions, right, because this is a consortium, this is a forum, let me know, or let one of us know, what's the farthest your rocket has flown.
Good.
I think we're going to need video evidence of that too, Divya. People are going to have to upload, the markings on the floor, the video of the rocket sailing to that point. Now, I don't trust these makers. They're very creative.
Yes, and since everyone is part of this, you're part of our team's group. So we're doing this ongoing community maker consortium. So you will be able to upload and share your files and things on the team site.
And go ahead and be creative and decorate them too while you're at it. Some flames or some racing stripes on the rocket would be awesome.
If you want to take this one step further, NASA's used the same idea, and they've created what are known as Stomp Rock. So they use the same idea of a bottle rocket, but they use PVC pipes and a little bit more connections, L joints and whatnot. And instead of squeezing it under your armpit, what you do is you stomp on the rocket, thereby imparting a lot more force, right? Forcing the air out much faster. And it turns out their rockets have flown quite a bit of distance too. So here's a link to NASA's Stomp rockets using the exact same technique. The ideas are pretty much the same, but they use a little bit more material. All right, so NASA does the same thing in their. We have something called the there's NCAS grant, where NASA takes community college students and then brings them over to NASA for short-term internships of sorts. So that's their pipeline to get community college students involved in NASA research, right? And a lot of my students have gone there through this pipeline. And so one of the activities they did was this. The Stomp rocket thing, which we had already done in class before. So that worked out pretty good.
So theoretically, Since the equation that you showed us only has the density, which in this case we're talking about air, the velocity, the speed of the air flowing through, and then the basically the cross-sectional area, the series of circles, of sliced circles that make up the long cylinder of the pipe itself as the air flows through all of those cross-sectional circles. But it does not mention the volume of air in our engine, which in this case is the bottle. So what differences would you expect to see if you were to only use a little 1 liter club soda tonic bottle instead of the full 2 to 3 liter soda bottle?
All right, so it depends.
Changed the amount of air, but we haven't changed the density, the cross-sectional area, or the velocity.
Sure. So you will have, so it depends on the size of the rocket. The size of the rocket that you can launch will change, right? For a little tiny bottle, for a tinier bottle, like a water bottle if you would, if you try to launch the same rocket as this, right? So even though air is not compressible, here's what you're doing. There's a whole lot more air in a 2 liter bottle than in a little tiny bottle. So think about it this way. And this was a really cool, that's a great question though. This was a really cool idea one of my professors threw out to us when we were first in an undergrad class. He said, water flows downhill due to gravity. Yeah, sure. So what happens if you have a tap on top of a water tank as opposed to the bottom of a water tank? So will you observe a difference in the flow rate? And we were all like, yes, you will observe a difference in the flow rate, because the one that's at top of the tank, right, it has only so much water above it, and one that's at the bottom of the tank has a lot more water. So there's not just quantity, there's also pressure involved in the situation, right? So at any interface, any water or air interface, at that interface, there are 2 different pressures involved. Or if you would, there's one pressure involved. The surface of the liquid is feeling a pressure. What pressure is it feeling? It's feeling atmospheric pressure, right? And to think about pressure, one way to think about pressure is the number of collisions these air molecules are having with respect to that surface.
Okay.
So now you think about this bottle, right? The number of air molecules colliding inside this bottle is a lot larger than the number of air molecules that are colliding inside your tiny 1 liter bottle. I don't have a bottle. I'm looking around for it, but I don't have one of those, right? So the pressure in both of those will be a little different, if you would. And yes, I've simplified this whole idea to just the continuity equation, yes. But yes, pressure is also involved in this. And so this builds up to another equation. So it's terrific. That's kind of the discussions we have in class. So same question, right? What happens if you have a tinier bottle or a larger bottle? Can you have a bottle large enough to launch a human being up into space?
As a math nerd, I always like that kind of question, because it's where you get to pull in calculus and everyone goes, oh, people who aren't math people go, oh, calculus, that I've heard that's hard. But
no, it's not.
Relating it to, something like this where you can demonstrate to them, since we're applying a different amount of air, we're going to run out of air faster. So the amount of air we can apply per unit of time to this rocket before it shoots off, if we can sustain the air, and so we're applying this pressure to this rocket for 20 seconds before it launches, then we get a better launch than if we can only give it 2 seconds of air pressure before it launches. And once you explain to people in a relatable, real-world made way that they touched and they held, I think we demystify the math and the science and show them, you understand this already. You see this at work every day in the world around you. You see it. You already understand it. It's not scary. It's not terrifying. You know how it works. You just don't know why it works the way it works.
Sure. And then this is the cool bit, right? So I teach math too. I teach math at TR. And some of the explanations I bring, some of the applications I bring from physics into math explains a little better why we do what we do with math, right? The convolution of matrices. We don't really do that in college algebra, but let's say there was a topic on convolution of matrices. Why would you do that? turns out you can use that idea to image process. That's the most basic idea in image processing. Right? Most images are presented in grayscales or pixels. So there's data, there's color data, and there's numbers associated with every pixel. They present as a matrix, right? And so the first idea in image processing is, how do you rotate an image? By performing matrix convolutions, right? So it's a really nice, there's so much relation between math and physics. It's just, which is why most scientists choose mathematics as a language to speak their science. Math is the language for most science. It's awesome.
Very good.
Next experiment we're going to do is a super cool experiment. This we do in our magnetism class. I will change my camera around. Let's see if I can do that. Device setting. There you go. And hopefully you are seeing what I want to show you.
We are seeing it.
Awesome. So the next experiment we have is a really simple idea. And to be honest, this idea I got from a YouTube channel by a female physicist. And I'm using female only because, it's one way to describe her. She's really proud of the fact that she's a girl and she does physics. So her YouTube channel is called Physics Girl. Okay, that's her thing, Physics Girl. And she explains a whole lot of complex ideas in a really simple fashion. Okay, so for this experiment, here's what I have. I have a stretch of copper wire. Insulated wire will not work. Magnetic wire will not work. This has to be naked copper wire. We'll explain why in a second. For this experiment, the best kind of battery that I have found works, and I've really done a lot of these. I used to play with this all the time, is a AA battery. There are a whole bunch of different kinds of batteries. There's AAAs. There's a mini AA that's half the size of a AA. You have a whole collection of batteries, right? But for this part of the experiment, I found that the AA works best. The magnets that I'm using are neodymium magnets, right? These are super strong rare earth magnets. Now, if you've used these magnets before, you know that every time you bring these magnets close together, they snap real quick. So I have had a lot of pinched fingers today just playing with these magnets. The orientation of the magnets around the battery is super important. So the idea is any magnet generates a magnetic field around it. Okay, I'm going to leave these magnets out. Any magnet generates a magnetic field around it. I want to try to share an image of the magnetic field for this setup. I do not know if you're seeing what I'm seeing.
No, we're only seeing the PowerPoint window at this point.
Just the PowerPoint window?
I'm still seeing the countertop with the magnet. It all depends on which screen you click on to magnify it.
Yes.
Okay, let's go to the screen.
Yeah,
Close up my...
It's sharing just the PowerPoint window, and if you have something else on your screen, it's only showing the PowerPoint window, not the other thing.
All right, so on the PowerPoint window, are you seeing what I'm seeing? A little magnet besides the battery with little field lines, if you would.
Yes.
Awesome. So this is basically what's happening. The magnet that we have, unfortunately, let's see if we can make a dark background on this. Not gradient, solid fill. Let's see if that makes it better. Okay, cool. So if you look at these magnets, right, here's your battery. Of course, I don't have an Energizer battery. I have some other battery. the magnets have to have this orientation: north-south, south-north. They have to be in an orientation such that they're repelling each other. This experiment will not work unless these two magnets, if you were just to take them out and bring them close together, they would repel each other, right? The reason it is this way is this: every magnet generates a magnetic field around it. One cool way to look at the magnetic field generated by a magnet is by using iron fillings. So if you place a magnet down on a sheet of paper, and you sprinkle iron fillings all from above, a little above, you notice that they orient themselves a certain which way. The reason they do that is they're orienting themselves along the magnetic field lines. Field lines are said to emanate from the North Pole and enter the South Pole. Right? That's just the regular way magnets are defined. As of now, in today's world, we do not have magnetic monopoles. All right, there was an experiment a few years ago that kind of sort of detected magnetic monopoles, but that was the only experiment. It was never able to be repeated. And that's the thing with science, right? Unless you're able to repeat an experiment, those results are invalid.
It was featured prominently on Big Bang Theory.
The magnetic monopoles?
Yes, Sheldon Cooper was interviewed on NPR to talk about that very topic.
Wow.
That's how I learned science, is Big Bang Theory.
Sweet. This is a true story. My PhD advisor always told me to watch Big Bang Theory. I've never have. Even to this day, I've never watched the show. But
oh, you really need to, Divya.
I will say I'm not really a TV person. I just didn't grow up with TV. It's not my thing. I would rather read or be outside exercising. But I had so many people over so many years tell me, have you seen Big Bang Theory? And I would say no. And they all said the same thing. You're so Sheldon. You're so Sheldon. You need to see this. And so years and years and years. And then when I finally, a friend said, I've got the DVDs, I'm going to loan it to you. And I started watching them. And I had to go back to her and say, I watched the entire first 3 seasons. And I have to say, Sheldon is totally right about everything. I agree with him on everyone else is wrong, and only Sheldon is actually precisely correct. It was very funny. I actually, the show, I think, does a pretty good job of dealing with science and dealing with the kind of people who tend to go into science. I was impressed. As a non-TV watcher, I still found it funny.
Yeah, it's a great show. But
fine,
that's
so
monopoles.
So magnets have dipoles, and this particular magnet, I'm going to go back to sharing my screen. The way this works, and it's a really cool explanation. I provided the link for the video from Physics Girl on this PowerPoint, and I'll share this PowerPoint later on as we finish this discussion. So she does a really good job of making it simple to explain what happens here. So here's what happens. The idea is to have these magnets slightly larger in diameter than the battery. Okay? So the idea is to have the magnets have a diameter that's slightly larger than the batteries. And the reason we do that way is because these magnets make contact with the wire. As this magnet enters the wire, right, it makes a really tiny circuit. This part is touching the wire, one segment of the wire. The back end is also touching a segment of the wire. So it, in essence, closes the circuit. And it's a really short circuit whose resistance, copper has a really low resistivity. So the resistance is really low.
David,
Yes.
can I jump in for a second? Could you maybe push your camera back a little bit, because it's kind of on mine at least, it's out of the frame. Like zoom it. Yeah. So I couldn't actually see what was in your hands.
All right. So here's the battery. I have made sure that when I place my magnets on my battery, right, that these two ends are repelling each other. These are neodymium magnets. I really don't want to flip them around because they snap together real quickly, even at that distance. So these are rare earth magnets. You get them at Hobby Lobby. Okay.
Or any place you can find magnets. We don't want to think Hobby Lobby is a sponsor.
So I'm not advertising for Hobby Lobby. It's just where I bought these magnets.
Any place you can find magnets.
I also got other magnets at Lowe's. So I found these at Lowe's. And then I found other magnets at Home Depot. So you can get them anywhere, pretty much. Amazon too. So the way this thing works is these magnets are protruding a little bit below the battery. So these magnets touch the wire and complete the circuit. So a lot of electricity flows. Now we have a rule in magnetism called the right-hand rule, right? So if there's a flow of electricity such in a circuit, right? So if you look at this wire, electricity is flowing this way. There's a magnetic field generated through the center of this slinky or coil, pointing this way, pointing in the upward direction. So electricity is flowing this way, magnetic field is generated that way.
Direction of your.
So that's exactly what's going to push this little train through. At all points, it's going to complete the circuit. And by the time this train comes out of this, right, it's going to be a little hot because it's been draining. There's a large amount of current flowing through this whole circuit. Okay, so now here's what happened. I tried to push the whole train in, and it pushed it back out. This is telling me that the orientation of the magnets is not correct.
Ooh.
Look at that. It pushes it right back out. So let's try one more time. It's doing nothing. So we change the orientation of these magnets. Oh, wow. Okay. Work. Okay, I didn't push it, but all I did was I made the slinkies go closer because there was a huge, there's a lot of gap between these little turns. And so it's not generating enough magnetic field. We'll try it one more time, see what happens. Let's see. And there it goes, come on. Oh. So this is what happens when you buy equipment on the day of the presentation and make it. Oh, come on.
So would it help if the coils were larger and closer together? Would that mitigate some of the problem?
So if the coils were closer together, that would fix some of the problems. If the diameter of the coil, right, was just about equal to the diameter of the magnets, that would help me too.
So you want the coil to be almost the size of the magnets, not much larger.
Not much larger.
Okay.
And a lot closer. That's going to help it too.
Mm-hmm.
And jump in, science nerd. The reason is because with things like this, the equations are a fraction and the radius is in the denominator, which means as you move away from whatever is generating the electrical charge or current, it gets weaker very quickly. Very, very, very quickly.
Right. So it's an inverse square law of force. What that means is, like Andrew just stated, it's the force generated varies as 1 by r squared. So it varies as 1 by r squared, right? So distances become super important in this experiment. The way I made this coil was using one of my little tubes. So the tubes I had, the equipment I had in hand, that's how I made the coil. Apparently that was not the best idea there.
So I'm going to throw this out to some of our attendees today. Let's say that Divya was doing this experiment with his physics class. What other classes could we combine with this physics that would add a layer of creativity to this experiment? It could, I'm going to get you started. What if we just did like an art class and they had to design maybe a casing for the battery to make it look like something else? What other classes can y'all think of that would be a nice pairing with this particular experiment? Go ahead and open your mics and jump in.
Let's try bigger batteries.
Or nobody? Nobody? Come on. Y'all supposed to be makers here. That's why you're on this call. Be creative.
No, that didn't work. Okay.
I could see you doing this with an art class, a theater class, and a literature class to reconstruct Dr. Frankenstein's lab and to make these coils and then to generate the electrical power as it goes down into the monster that Dr. Frankenstein creates.
What if you used the coils as some sort of symbolism for philosophy of some sort about what moves people? Could you take the action that's going on and look at some of the metaphors that go along with it.
That if magnets aren't oriented correctly at the beginning, then you don't get the motion that you were expecting. So you have to orient.
That's a life lesson right there.
Yeah.
Have the proper motivation in life, you don't get the results you expect.
Danielle, Scott here.
Hey, Scott.
So earlier with bottle rockets, Frank was talking about the equations in calculus, and it made me think of, what that does is it makes knowledge of the world around us available to us through symbols.
Mm-hmm.
Am I correct? Because I'm not a math guy.
Yes.
But in literature, there are a school of thought and philosophy that we can't actually know the world firsthand. We can only know it secondhand through signs, symbols, and metaphor, which I think is one of the great attractions of calculus.
Yes.
So I can see a discussion easily going in from these experiments when you start marking these symbols on the chalkboard. Like, okay, what exactly are we doing? We're marking symbols. Who came up with these symbols? How do they mean what they mean? What is the nature of meaning? That is not science. It can't possibly be science. It can only be dealt with in the realm of the humanities. Thank you. I'll shut up now.
I mean, you could even include a history class on where, each of these items comes from. I mean, who made the first magnet? Where does copper wire come from? I mean, when you're talking about manufacturing, you're talking about history and development and mankind. At what point in history did we first develop the magnet? I think I would hate for people to think this is only a physics lesson. There's so many things you could pull into this one experiment and combine and really show how all of the disciplines interact with each other. And that's really what making is all about, making maker spaces, as we're talking about. And he's going to keep perfecting this.
I'm sorry.
No, keep going. I'm fascinated. I'm trying to see what you're doing.
I think, Scott, actually, the kind of goes to what I was saying earlier of, since we start with procedural arithmetic and algebra, people never get to the really cool, powerful, interesting math. And actually at the higher levels of math, where you get into where math really does become number theory and proofs just as much as it is equations, where you're actually having to define, well, why do we work with integers? What is integerness? What exactly is multiplication? What does that mean when we multiply? How do we know that works? And you actually, the language becomes less numbers and equal signs and more sentences, although there's still a formal mathematical logic syntax of different symbols that mean different phrases. But you really are reading sentences. There is a convergence between philosophy and math at the higher levels of how do we know that these things exist? Well, we kind of don't. We kind of assume they exist because they work, and we all agree, here's what we're going to say an integer is. We don't really know out there what it actually is, but here's our definition. Here are rules. We're going to work within this set of rules. And different kinds of math work differently within different conceptual rule sets, the same way different philosophies work differently within different kind of schemes of belief.
Scott, you were saying something?
Oh, I don't know. I forgot.
I do think that if we bring applications of mathematics into math classrooms, right? Because right now the way we do math it's extremely pedagogical. It's like, oh, here's the equation, here's how you solve the equation, this is what you do with that equation. And somebody sitting in the math class, he's learning a lot of math, maybe, or falling asleep. I don't know, one of the two. But they're always questioning. There's like, when am I ever going to use this math? Where am I going to use this math? That's a question in the back of everybody's mind, right? It was at the back of my mind when I went through a math class. And so if you bring in applications, right, for engineering students, most college algebra students, some of them become engineers, some become nurses. So most of them are going to apply this at some point in their life.
Right.
So if you bring in the applications, forget the higher level discussions, right? Because math can become abstract pretty quickly. You bring in simple applications. Bring the same experiments we do so happily in a physics class, right? Because I don't have enough equipment here to do my experiments, and that makes me a little sad. But the same experiments we do in our physics class, if we did that in math class and showed them the application, right? Okay, so sure, you're finding the area under the curve. What does that mean? Show them meaning to the math. I'm sure they'll take to it faster and they'll retain it a lot longer. It's just an idea. It's just a thought.
The beauty of maker spaces, when we're talking about maker spaces, is that they are a space where you can bring together people who have different backgrounds, where you share information. So somebody like myself who does not have a background in science, and honestly, while I see this cool, wonderful experiments that you're doing, Andrew just killed the cool by putting in the math, and that just
No.
No, the math, I don't care. It's just cool. Let me just have fun with it. But if I were to partner with someone like Divya or Andrew who understood the math, and I came in with my creative side, together we can come up with something that neither of us could have done on our own. And that's the beauty of makerspaces and these environments where we're bringing in people with different interests, different abilities, different points of view, and we come up with things that are so much than any one of us could have done individually. So that's what I love about makerspaces. That's why I'm so passionate about those.
Yeah, something I would love to do if I could completely redesign K through 12 from the ground up when it comes to science. Here's something. I would take a bucket, cut a hole in the bottom of the bucket, suspend it from the air, put a spigot of water with water flowing into the bucket, and then have the students turn the water on and more, turn the valve on until we get to a point where the level of water in the bucket stays constant. That is the amount of water coming in from the spigot into the bucket, and the amount of water draining out of the hole at the bottom of the bucket is the same, because the level of water in the bucket never actually changes. We're gaining water as fast as we lose water. That's a simple kind of fun, hey, see if you can equalize these things. What they don't realize is 14 years later in your college physics class, you'll actually learn all of the equations in calculus class for exactly how that works and why that works. And I think if we can get them in a lab, and if we can get 6-year-olds in a makerspace and say, hey, play with this bucket of water and let's see if we can do something magical. Let's get the level of water to never change in the bucket. I think that gets a natural excitement that later on stays with them. And later on, when they encounter that situation, instead of going, oh, you just killed this by bringing in the math, they're like, oh, now I see how that works. It's magic. I'm Harry Potter. I know how the magic works. I know exactly how this magic works.
Mm-hmm.
Somebody was talking about the history, tying up history with science, right? And
Yes.
That is an amazing thing, because you need to know how you failed before you learn how to succeed.
No. We have to speak the right language. It's not what failed. It was just the first way that didn't work. That's
Right.
not a failure. That's a discovery. So the first thing you figure out is all the ways that don't work till you get to the way that does work. So it's not a failure. And my example yesterday was that WD-40 is called that because the first 39 ways didn't work. Number 40 worked. So
This is Scott.
Wow.
In art, and I suppose to a certain extent in the other performing arts and dance, we don't call them, we call them happy accidents. And when we have enough of them, we call it a body of work and we're ready to exhibit.
That's good.
yes, indeed.
That's pretty
I
good.
like Jennifer's comment. Jennifer Jackson in the comment section put, I was going to say art, but what about speech class as part of the demo? And that would be a good way of bringing together a group of people and showing them, hey, who's a maker? You are a maker. And so you combine the people who can do the production, who can produce the speech, and then the people who can do the equations, and then the people who actually like the arts and crafts of cutting up the coils in the PVC pipe, which I love the physics and the math behind it, but man, I have no interest in creating the coil itself. That to me is, I would love to farm that out to Danelle and let her craft the equipment
Absolutely.
all day long.
I'd be all over that.
So with this metal, Divya, if you're still there, with this metal, obviously we need something that can conduct a current. So what kinds of metals can we obtain at the consumer level that that will conduct the current we need for this train to work?
Sure. Copper is one great idea. Steel will work. Any kind of steel wire. And so that was going to be my next bet. If I didn't find copper, I was going to go use steel, and it works just as well with steel.
And don't you have one more experiment for us today, Divya?
Yes, I do. It's more of a discussion rather than an experiment. So I love coffee. I really do. I love coffee. I love
Do
tea.
you want to switch your camera away from the coil?
Sure.
Coil still.
Let's do that.
I still
But
see.
I love the discussion. You know, I mean, I am loath to walk away from the stuff.
This is why you have to watch Big Bang Theory.
It is a very playful series. It does a good job of bringing the fun in science, the playfulness of it.
I will say I have learned all about Schrodinger's cat thanks to Big Bang Theory.
You have you? So
Now I understand it.
What is it about Schrodinger's cat?
Oh, it's just the theory that we don't know something until we know it. It's yeah. I'm not going to explain it.
Perfect. No, that's exactly right. You are 100% right? So the whole idea about Schrodinger's cat or any measurement is, if you don't see the moon, is the moon really there?
Although my favorite comeback to that was when Penny said, well, that some cat had been trapped in a box and we didn't have to open the lid to know that cat was all kind of dead.
So there, recently, there was a new paper published on a new take on Schrodinger's cat. You know, like there was a new take on that whole experiment. So there's a journal article out there about Schrodinger's cat. Schrodinger's cat is still making trouble.
And if you don't know what that is, go watch Big Bang Theory.
Well, it does tie back into something that Scott said about how do we know what we know. That's the basic underlying of Schrodinger's cat is when we do the measurement of something, we are interacting with it. And so by interacting with it, we potentially affect the measurement. So are we actually ever truly measuring the real thing? Or are we simply through a 1-step, 2-step, 3-step remove process? Are we ever fully directly interacting with the universe, or is everything filtered through some level of we had to know it? The knowledge had to come to us somehow through some medium. And that's the essence of Schrodinger's cat is when we make the measurement, that's when we actually make the thing happen that we measure at the same moment. So it might have, before we measure it, who really knows what state the world was in until we turned and looked at it.
Is that
right? So the measurement itself made the event that you looked at past.
Yeah.
Does that make sense? So if you were trying to track the position of an electron, you use there's 100 different techniques out there, but let's say you use scattering or some such experiment to measure the position of an electron. By making that measurement, you have changed the position of the electron because you bombarded the electron with other particles, and that therefore changed the position. So now what you know is, was the electron there at some previous time?
You see, the problem here is it makes your head hurt. So this is why we have artists, and so all we do is we just go make a movie like Salvador Dali did, and explains everything.
Or Big Bang Theory, go make a TV show.
That won't blow your mind. Salvador Dali will take away by blowing your mind.
Wow. All right, so let's get to my favorite part, drinking coffee. Yes, this is my little Star Wars mug. So the idea about coffee, right? And then this is the discussion we have about coffee. When you mix two fluids, for example, if you mix coffee and creamer, I can't really show you because my cameras are not positioned such. But hopefully you all have a cup of coffee in front of you, or tea. And if you add a little creamer and you start to mix your creamer, right? As you stir, you notice there's a distinct separation in the two fluids for a little bit, right? Now, if you start stirring faster and faster and faster, what do you observe? You observe a little dip form in the center of your coffee. In the center of your cup, there is a little dip forming. All the fluid is going towards the walls. So when you start to stir your coffee or tea, right? What are you doing? You're pushing the liquid with the spoon. That's exactly what you're doing. You're pushing the liquid with the spoon. But there's only so far that liquid can go, right, before it meets the side of the mug. If you did the same thing, this is really extending the idea out there. If you did the same thing with a spoon in a swimming pool, right? The water spoon would move forward. It would keep going forward, right? Why would it keep going forward? Because the swimming pool is so large, right? Nothing would ever happen. Eventually, after enough time had elapsed, maybe there would be a little tiny wave at the end of one of the corners of the swimming pool. But in the mug, we see what we see. We see this whole little depression form, right? Why? Because of velocities. And this is a great segue into velocity for rotation, rotational velocity, angular velocity, so to speak, right? So if you, for example, you're riding a bicycle. If you're riding a bicycle and you look down on your wheel, you see that the wheel is rotating. If, on the other hand, your significant other or your dog were standing on the side of the road looking at you riding a bicycle, what they would observe is slightly different. What they would notice is they would be able to see the bottom spokes of the wheel a lot more clear than they would be able to see the top spokes of the wheel. And that doesn't really make intuitive sense, but that is how it is. You can take a picture, a photograph of a bicycle wheel, and you will see that the bottom spokes are in focus and the top spokes are out of focus. And the reason that is because the bottom spokes are slower, or the bottom part of the wheel is traveling slower than the top part of the wheel. And you may be wondering, really, what? Right? Why do you think that is? Because here's the whole cool idea. When you're riding a bicycle, right, hopefully you're not slipping. You're not slipping on the road. Slippage is not taking place. So yay, friction. Friction that we all hate every day, right? Friction that makes our life so horrible, that increases our electricity costs and everything. Yay to friction is the reason why we're not slipping. And so because of friction, because there is no slippage, right? There are two distinct motions happening. We call these motions translational motion and rotational motion. Rotation is the wheel spinning around its central axis. And translation is the whole bike moving forward. If you didn't actually see the wheel spinning, right, you would just see a bike moving forward. All parts of the bike would be moving forward at the same velocity. And the cool idea about physics is, right, you can break that problem down into two parts. You can break it down into a rotational part and a translational part of the problem. So let's come back to our coffee. Right? So when you are moving your fluid around in little circles, you're imparting some velocity. If your mug broke, right, you were stirring so fast that your mug broke at that instant, what do you think would happen? The coffee would fly in all directions if you continued stirring, right? Why is that? Because here's the thing, inertia is this awesome idea, right? That any body that is moving in a straight line continues to move in a straight line. Same with your coffee. If your coffee is moving in that direction, it'll continue to move in that direction as long as there's no cup. But there is a cup to block it, which is why you go around in little swirling circles. Where else do you see this idea of swirls, right? You see these swirls. If you were ever to go to space, and I really hope all of us get that opportunity someday, if we were to go to space and we look down on a storm cloud forming, you would see the same exact pattern. You would see these little swirls form. So then here's the question, right? For a coffee mug, sure, there's a solid wall, there's a solid surface. Why is my storm cloud forming in the same pattern? Right? That's the question you have to ask. Why? Why do you think that is? Densities. And that's the same reason when you put in creamer into your coffee mug, right, the liquids don't mix together at the same time because they have different densities. If you want to take this idea a little further, right, they're also at different temperatures. Here's the coolest thing about temperatures, right? When we solve temperature conduction problems, we don't solve 3D temperature conduction problems. We solve what are known as zero-dimensional temperature conduction problems. Why? Because the math is so hard. So we have these awesome software out there, ComSol, SolidWorks, whatever, MATLAB. We use all of these to solve zero-dimensional conduction problems. And whatever knowledge we gain from that zero-dimensional heat conduction problem, right, we extrapolate into our 3D world. And so the question is, how accurate is that? Does that even make sense? all of our chips, all of our computer chips, everything that we work on, our phones, our chips, everything, they generate heat, right? They use electricity, they generate heat. Heat is the limiting factor there. So you have to get rid of the heat. How do you get rid of the heat? In our computers, you have these little fans on the top, right, that keep spinning on top of your chip. And you have a huge metallic little heat sink, if you would. You have a little metal frame with a fan on top. So it generates its own flow channels and whatnot. It tries to cool the chip, right? So then you may ask, okay, water cools everything so much faster. Why don't we just put water on the circuit, right? Why is water not a coolant? Because water conducts. Okay. Can we not have any other liquid that's not a coolant, that doesn't conduct as a coolant? Sure we can, but here are the conditions, right? That liquid has to be non-compressible. We talk about non-compressibility. What is non-compressibility? When you put water in a container, right, and you start applying a lot of pressure, the idea or the assumption in basic physics or science or anything, or including your coffee cup, the assumption is that water is not going to compress any further. Its density is going to stay constant. Right? And so when you're mixing your creamer into coffee, these are the thoughts that are going through my head. I don't know what thoughts are going through your head, but these are the thoughts that are going through my head. I'm like, why is it not mixing faster? Right? Why is there that distinct layer? That creamer and the coffee has a distinct separation. For a little time, they do have a little separation, right? There's a little wall, if you would, that separates these two liquids. For a little tiny bit. So why is there that? Right? So where else is this idea used? We use these ideas to launch satellites. The same idea that we used for velocities, right? Translational, rotational velocities. We use the very same idea to make our life launching satellites easier. If you notice, throughout the Earth, the places where we launch our satellites from, they're distinct. There are certain places where we launch rockets from. Why is that? Right? Because the Earth is spinning. Earth precesses. It goes around its own axis, right? It precesses. And that's imparts some sort of rotational velocity to the whole thing. So if you launch from certain places, right, you take the benefit of all that rotational velocity. If you launch in a certain direction from certain places, you already have done some of the work that you need to do by burning fuel. And so I'm going to drink my coffee and enjoy it right now, but that's the kind of thinking I have. And so physics is everywhere. Just like math, physics is everywhere. And it's really cool. I see physics in everyday things, right? Every time I sit by my window, I see dust particles float around there. I think about it. What do you guys think about it?
And of course, Scott sees all that as art.
So it sounds like you're saying we have a more advanced space program than Canada because we have equatorial privilege.
Oh, I got it. Okay.
Because Canada is too far north to launch. You
Gotcha.
lose the mechanical advantage of the rotation of the Earth. You need closer to the equator.
Right. It's not that Canada cannot launch. It's just they have to burn a lot more fuel.
Right. We have equatorial privilege that they do not have.
We do. We're special that way. We're Americans.
But we still had to go all the way to Florida and Houston to do it. We couldn't do it from the Midwest either. Not easily, cheaply.
Oh my gosh. I think that's a great way to wrap up today. Andrew, you want to finish it out?
Sure. Well, thanks to everyone for joining us. We hope you enjoyed working through some of these experiments and making some of these things, putting into practice knowledge that we have. We are recording all the sessions, so of course you can come back and check on these later if you'd like to work through these with a child or colleague or superior. We will be having more sessions throughout the week, of course. Tomorrow we have Barb Mueller, who will be doing the morning session that's at 11 a.m. Central Time. That's a conversation about badging in all of its forms and for all ages. So it's kind of the transition away from a full 4-year degree or a large technical certification into specific badges that apply to maybe you've learned to do a specific thing, and that thing has value, and a badge that kind of demonstrates that you have that ability. Sort of like what a lot of people in makerspaces deal with when, how do we know when it's okay to let someone loose on the laser cutter or the CNC or whatever, and badging is one way to do that. We'll have another networking activity tomorrow afternoon at 2. So we hope you'll join us. And of course, all that information is back on the main MakerCon page. We are adding everyone. You'll all be part of our ongoing MakerCon consortium. So this conversation will continue, and we'd love for y'all to participate. If you do some of these projects later on, please do upload them and share them with us. All right.
Thanks,
thank you all.
everybody. Have a great
very
afternoon.
much. See y'all tomorrow.